These are the 7.3 notes, and we're going to be looking at sample means. So a sample mean and a sample proportion, they look very similar. And when I was first learning about the sample proportions and the sample means, it was kind of difficult to determine, wait, why is this different? Why is the sample proportion something that's different than the sample mean? Well, the kind of like simplest and shortest answer to that is the sample mean. The formulas that we're learning right now, and everything that's going to come in these future notes, it's all based off of a quantitative stat. So something that we have like hard numbers on that we can actually look at. So we're looking at averages, we're looking at standard deviations, we can look at the actual ranges of things. So it's based in like a quantitative stat we can actually take. And then a sample proportion is based on a yes or no question, so a success or a failure, about how much a population engages or doesn't engage in the area we're curious about. So the easiest example, the book talks about like how they're using height for a lot of it, height of girls in the United States. That's an actual quantitative measure. We can figure out what are the exact heights of women in the United States. We can figure out those averages. We can get the population average. We can go on from there. What we can do with and then with proportions, that's different. We're not saying like, are you tall or are you not tall? I guess we could define like one very specific measure of if you're over 6 feet or if you're under 6 feet, because that's a success or a failure. And then we could figure out the proportion of the United States that's above 6 feet, and then we could figure out the probability that we get a group of people who are above 6 feet in an average. We can figure that out. That would be a sample proportion. But that really doesn't tell us all that much. We're actually going to be a lot more curious about the sample mean. Here's the actual heights of women in the United States. Here's the actual average. Here's the actual heights around them. How can we figure this out? All right, so the mean and standard deviation of a sampling distribution is broken down by these formulas. Exact same thing as the sample proportion. So the mean of the sampling distribution, the mean of a sample. So if I take a group of 10 girls and we do that over and over and we do the entire population of the United States, the mean of that sampling distribution is going to be equal to the mean of the population. So the book says it's 64.5 inches, same thing. The mean of the sampling distribution of women's heights in the United States is going to be 64.5 inches. If we take every single sample over and over and over again, we're going to get that mean as an unbiased estimator. Standard deviation is going to be the standard deviation of the population. And then we're going to divide it by the square root of the number of our sample size. So the standard deviation of the sampling distribution will change based off the size of the sample size. Same thing that we've been seeing, that the larger sample we have, the less variability within that sample population. So because we have less variability between our samples, we would expect our standard deviation to shrink when we have a larger sample size. So we're looking for a larger sample size there. And then we have to make sure that the 10% condition is satisfied here, because again, we want to make sure everything is roughly independent. If we don't have a 10%, if we're going above the 10% sample size, then we no longer are really looking at an independent population. And because of that, that skews it. So when we're taking these sample sizes, we need to make sure it's less than 10% of the population still. All right, if we sample from a normal population, basically, then the sampling distribution of the sample mean has a normal distribution. And this one does not matter the size of your sample. As long as the sample is multiple people, as long as we have samples that are 2 or above, it's going to have a normal distribution. The sampling distribution will be normal, just like the population distribution will be. And then the standard deviation will be based on the formula that we saw above there. And then again, this is as long as that 10% condition is met. So again, with a normal distribution, your sampling distribution will always be normal, and regardless of the size of your sample. And then it will have the mean, the sampling mean will be the same as the population mean. So basically I'm saying sample mean is equal to population mean. The standard deviation will be equal to standard deviation over the square root of n for that sample distribution. So let's go ahead and look at this and check for understanding. So the length of human pregnancies from conception to birth varies according to distribution that is approximately normal, with a mean of 266 days with a standard deviation of 16 days. Find the probability that a randomly chosen pregnant woman has a pregnancy that lasts for more than 270 days. So what we're going to do is Set up. 270 minus 266. This is the normal z-score population. Okay, 270 days minus the 266 days over the 16-day standard deviation. So that's 4 over 16. So we have a 0.25 z-score. And then since we have a 0.25 z-score, what that means is that, looking at my table A here, so 0.25. So that means 0.5987. This is the proportion of the population that has a pregnancy that lasts 270 days or shorter, because again, this is covering this part of that normal distribution. So it looks like this over here. So if we want to figure out the 270 days or more, we have to do 1 minus 0.5987. And when we do that 1 minus 0.5987, we find that this will be 0.4013. So there's a 0.4013 probability that if you choose a random pregnant woman and you find out how long her pregnancy was, you're going to find out that there's a 0.4013 probability it was 270 days or longer. All right, so now suppose that we choose an SRS of 6 pregnant women. Let X equal the mean pregnancy length for the sample. So here, it's still just going to be equal to the mean of the population. The mean of your sampling distribution, this should be an unbiased estimator. The mean of your sampling distribution should be equal to the mean of the population. So this is still going to be 266 days. And I just explained that for 2. So it's a 266-day mean because of the fact that this is an unbiased estimator. Mean of the sampling distribution is going to be the same thing as the mean as the general population. Compute the standard deviation of the sampling distribution. Check that the 10% condition is met. The 10% condition is definitely met. 6 pregnant women is significantly less than 10% of all women in the world who are pregnant currently. So, or who have ever been pregnant. That's a very, 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 very easily stated fact that we've met the 10% condition. So here our standard deviation is going to be, the standard deviation of our sampling distribution is going to be the 16 days of the regular sampling, or of the population standard deviation, and then we're going to do it over the square root of 6 because that's our population size. And we're going to find that our standard deviation is roughly 6.53. So now, what's the probability that the mean pregnancy length for women in the sample exceeds 270 days? So now we're going to do the 270 minus the 266, and as opposed to being over 16, it's now going to be over 6.53, because again, we have this group, and since we have a group, our pregnancy should be closer to the average. The average of that group should be theoretically closer to the average, because we're taking those extremes. So if we have one woman who's above 270 days, we filled out that 40%, well then we still have that 60% chance of a woman under 270 days, kind of bringing that average down. So that standard deviation drops, so now we're looking at 4 over 6.53. So our z-score is now 0.61 for a z-score, which means that our proportion is 0.7257. But again, this describes the left side. This is everyone with this describes pregnancy mean lengths of 270 days or less. That's represented over here. So that means if we want exceeding that, we have to do 1 minus 0.7257. And that means that there is a 0.2743 probability that if we took a group of 6 women and we took the average of their length of their pregnancy, it would be above 270 days. So that's still a pretty good probability. That means we shouldn't be shocked if we have a group of 6 women and their mean pregnancy length was, like, let's say 271 days. There's a 0.2743 probability that it's going to be greater than that. So if it's at 270 days, we say, okay, this isn't shocking given the length of pregnancies, the standard deviations. This is a relatively small sample size, so Since it's a smaller sample size, yes, it reduces the standard deviation from if we were just to find one specific woman, but it's not going to reduce it at a huge order. That's why when we take that larger sample size, our mean is going to be much closer to what the population mean is. Central limit theorem and sampling and non-normal distributions. So the book does a good job of explaining this, and I'll just kind of go into it. If we have a very skewed distribution, we cannot just say that the sampling distribution is going to be normal. If we have sampling distributions with small numbers of skewed distributions, it's still going to have a skew in that sampling distribution, because we still have that chance of, okay, let's say something's heavily skewed to the right. We're talking about salaries. So let's say that and my sample size is only 2. If I choose Jeff Bezos' salary, literally combined with anyone else's, it completely skews that sampling distribution. It is just going to crazily drive it out of the average. Or if I choose, like, let's say Bill Gates' salary and somebody else's, it's just going to completely skew those averages, and it's going to still skew it to the right. If I take a sample size of 30, sure, the Bill Gates sample is still going to be the largest one, or the Jeff Bezos sample is still going to have a number that drags it heavily to the right, but then I'm much more likely to get a lot of numbers that are going to pull it towards that mean. And so the book talks about, like, they kind of go through, they show you making a sampling distribution of something that's heavily skewed right and then changing the sample size. Once you start hitting the low 20s, that sampling distribution starts looking normal. But just to be safe, the book says if we are taking data from a skewed distribution, if you have 30, if your sample size is 30 or above, that sampling distribution is going to be approximately normal. Not exactly normal, but approximately normal. So as we go through, even if we have a heavy skew, the sampling distribution will still be normal, because if our sample size is large enough, because the larger the sample size, the less variability we have person to person. So we get those averages closer and closer to what the actual mean will be. So we can look at the normal distribution, we can figure out the probability of a group of 30 houses and what their household income would be, or a group of 30 people, and figure out what's the probability that these 30 people have an average income greater than or less than this number. What's that probability? We can go through and do it by groups. We can do it with a little bit more, and we can do it with a lot more accuracy than individually, because we have got a normal distribution that follows normal distribution rules, and we have those proportions for normal distributions. Everything else from here is the same. So once you have a sample size above 30, we're going to treat it just like I treated it in this example up here. So that's the main difference with the sample mean, is that if we're doing a sampling distribution of a normal distribution, your sample size can be whatever, and you can use normal approximations, because a normal distribution is always going to have a sampling distribution, which is also normal. If you have a distribution that's not normal, though, you have to get to a sample size of 30. And once you're at a sample size of 30, then we can start using normal distributions, a normal approximation for a sampling distribution, because we've centered things more around the mean. And that's the central limit theorem, which is just stating that the larger and larger we get our population to be, or the larger and larger we get our sample size to be, the closer and closer we get to that average mean in our sampling distribution. All right, you guys have a homework assignment tonight. If you have any questions or concerns, please reach out, and have a great night.